The action.
X1. Uh, can you hear us?
Yes, can you see my slides
Yes,
on my?
you can. Okay, the floor is yours.
Okay, thank you so much. Good morning, everyone from here in US. Good evening to everyone across the globe in Europe and elsewhere. Thank you for giving me the opportunity to present at this workshop. So my name is Aditya Upreti, and I'm going to be talking about the recent results from the MoEDAL experiment and the first experimental search for production of magnetic monopoles via SCHWINGER mechanism. So just to give a brief overview, a lot of this has been covered in the previous slides, and some of this might overlap. But magnetic monopole is a hypothetical fundamental particle with an isolated magnetic charge which produce a magnetic field. There are several motivations for the search of magnetic monopoles. There is no fundamental reason why an individual magnetic monopole would be forbidden in our universe. It would lead to symmetrization of the Maxwell equations from the duality symmetry and the quantization of electric charge coming from the Dirac's quantization condition, which says that if at least one magnetic monopole exists in the universe, then all electric charge would be quantized. Stemming from that Dirac quantization condition, we have the equation of the fundamental charge of magnetic monopole in terms of the electric charge. And again, stemming from that, you have monopoles, which are highly ionizing particles. Now, monopoles are predicted to exist in several theories, like the grand unified superstring and quantum gravity theories. You have the Hooft-Polyakov grand unified monopoles, which have a mass of the splitting of the grand unified force. And then you have intermediate mass monopoles, which are produced in the intermediate stages of spontaneous symmetry breaking. There is a Cho-Mason monopole, which is the electroweak monopole in the Glashow-Weinberg-Salam theory, which is of the few order of a few TeV, which should be accessible to the colliders. And then there are dions, which are particles having both electric and magnetic charges, which are predicted by Julian Schwinger. And a recent search of MoEDAL focuses on dions. So the MoEDAL experiment, just to give a brief overview about it, it's the seventh experiment at the LHC. It's the first dedicated experiment at the LHC for the high-line ionizing particles. So it searches for magnetic monopoles and other pseudo-stable particles. It comprises of two passive detectors, the magnetic monopole trappers and the nuclear track detectors. The magnetic monopole trappers are aluminum trappers, which are predicted to trap monopoles. The nuclear track detectors are macrofoil foils, which are stacked along, and they are sensitive only to new physics. There is the active part of the model environment is the time-pix detector, which monitors the spallation products and is the only active component of the model experiment. Um, so I'm going to be talking about the magnetic monopole trappers. They're basically 800 kilograms of aluminum bars, which are stacked in different sections of the model LHCb region at the intersection point 8. So the idea is that the MMTs, the magnetic monopole trappers, are predicted to capture a magnetic monopole due to its interaction with the magnetic charge of the monopole. The interaction of the magnetic charge of a monopole with the magnetic moment of the aluminum nuclei. So if the magnetic monopole has an energy which is in the range of zero point 0.5 to 2.5 MeV, which is less than the binding energy of the aluminum nuclei, then it would be captured in the atomic lattice. Now, these aluminum trappers would then be analyzed by the superconducting quantum interference device, the SQUID interferometers, and a persistent current in the superconducting coil would be induced by a magnetic charge and would lead to the presence of a magnetic charge. Now, how are these devices calibrated? There are two calibration methods which are used. One is the convolution method, where you add measurements from a dipole sample to get the response from a magnetic monopole. The other one is the process which measures the magnetic pole using a long thin solenoid that mimics the charge of a known monopole. So these are the two methods which are used for the calibration of these devices. Moving on to the next type of detectors we have at the MoEDAL experiment. These are the nuclear track detectors, which are several stacks of macrofoil foils and These are basically read out by optical scanning microscopes. So as a highly ionizing particle passes through these entities, it would leave a damaged track. And these tracks can be later reconstructed and measured using the chemical etching process. So it would leave a damaged zone, which is shown in the picture below, and then these can be analyzed. Now, the good thing about the entities is that these are virtually, due to the high threshold properties, these are virtually background free because they remove the low ionizing radiation. And the heavy ions are stopped because of several radiation lengths between the beam pipe and the nuclear track detectors. The magnetic monopole trappers, because of their highly ionizing properties, can punch through several layers of these MMTs and therefore would lead to a signal in our detectors. So on the basis of these, the magnetic monopole trappers, MoEDAL had published the recent results for the 13 TeV PP collisions, and these were interpreted using two methods. First one was the usually used Drell-Yan production method, and then it was enhanced by the photon fusion mechanism. So on the basis of those two methods, we have world-leading limits for magnetic charges from 3 GD up to 5 GD, and again, the breast cross-section limits. For the lower charges, 1 GD and 2 GD, they were eclipsed by the ATLAS results for the 13 TeV experiments. But the run-free estimates for the PP collisions are predicted to produce the best cross-section and mass limits at any collider experiment. So that's something to look forward to. Now, an important point about these limits are these are calculated with Feynman-like diagrams, and they do not account for the non-perturbative nature of the large monopole photon coupling, which are used in these calculations. Then there was the search for dions by the MoEDAL experiment. This was the first search at any known collider experiment for the dions, which are predicted to have both electric and magnetic charges. It was 6.46 from the Bond inverse of 13 TeV collisions for the proton-proton run. And we placed the first mass limits for the search of dions from 790 to 1330 GeV for magnetic charges up to 5 Dirac charges and electric charges from one equivalent of 1 electric charge to 200 electric charges. So this brings an end to the review of the past MoEDAL experiments. Now I'm going to be talking about the SCHWINGER mechanism, which deals specifically with the heavy ion collisions. So just to give a brief overview of SCHWINGER mechanism, it is the spontaneous creation of electron-positron pairs in an extremely strong electric field, which arises from these pairs quantum tunneling from vacuum states to existence. It is a non-perturbative effect, which means that the rate can be calculated non-perturbatively using semi-classical techniques. And so this was studied for the electric charges. Now, using the electromagnetic dual of the SCHWINGER mechanism, the same process can be used to study and search for magnetic monopoles in the presence of very strong magnetic fields, the likes of which can be produced in heavy ion collisions. So before moving on to heavy ion collisions, I just want to list a couple of advantages of the SCHWINGER mechanism. First is the strong coupling issue. So the previous searches, like the Drell-Yan searches, because the monopoles are strongly coupled from the Dirac's quantization condition, the perturbation theory can only give upper bounds on the cross-section, which are used for comparison between different experiments. The SCHWINGER pair production process, because of its non-perturbative nature and the rate being calculated by the semi-classical methods, does not have faces the same problem as the other methods for calculation of monopole cross-section. The exponential suppression, as Professor Ajante had discussed earlier, does not apply directly to monopoles produced from the SCHWINGER mechanism because it's not being produced in elementary particle collisions like the PP collisions, which are exponentially suppressed by the factor, which is a very large factor. So where these monopoles would be produced is the heavy ion collisions at the Large Hadron Collider, which produces the strongest magnetic fields in the known universe. These are of the order 10 to order 20 Gauss, which is 4 orders of magnitude larger than neutron stars and magnetars. And these are basically produced in ultra-peripheral collisions at these at the PBBP lead ion run. These are produced for a very small time, which is given by the inverse decay time of the fields, but these are extremely strong. And if we have an empty state initially, you have the magnetic fields, the strong magnetic fields. You could have a final state which has magnetic monopole pairs, which are produced in these strong magnetic fields. So just to so our search needs to have the Schwinger kinematic distribution and the cross sections, and then we have the trapping detectors, which would give the trapping acceptance. So just to start with the kinematic distribution for the Schwinger mechanism, we use the free particle world line approximation at the LHC energies, which was given by the co-authors, this Professor Jante and Gold and Ho. Um, the space-time dependence of electromagnetic fields, which is very important at LHC energies, is treated exactly. The momentum distribution is primarily due to this time dependence of the electromagnetic fields of the heavy ions, which gives an isotropic momentum distribution. The monopole-antimonopole interactions for this free particle world line approximation are neglected. But because the momentum distribution is primarily due to the time dependence, this is a fairly good approximation for the kinematics of the magnetic monopoles. So we use the free particle world line cross section, which is given by the following formula, and you have the cross section which decreases as the monopole mass increases, which is fairly understandable because higher mass monopoles would be difficult to produce, and so this would be a linearly falling, exponentially falling cross section with the increase in masses. Now, the strong coupling effects, which are neglected in the FPA cross-section, would enhance the monopole production probability to all momentum and increase the cross-section exponentially. And therefore, this cross-section approximation, the Schwinger free particle approximation, can be considered a lower limit on the overall cross-section for the magnetic monopoles. We also have the locally constant field approximation, which assumes a locally constant field. So the space-time dependence of electromagnetic fields is treated perturbatively, but the strong coupling of the monopole photon coupling is accounted to all orders. Uh, the space-time dependence would enhance this cross-section of like the previous one. Um, and this cross section, the important factor about this important aspect of this cross section is that it's highly mass dependent. So the cross section varies very widely with slight increase in masses. And increase in the magnetic charges for different GD. So here I have plotted the range of masses that could be considered for different monopole charges from this cross section. So both locally constant field approximation and FPA are complementary to each other, and both would give a conservative lower limit on the cross sections. So an improved theoretical cross section calculation would give stronger bounds compared to both of these approximations. Now, the Monte Carlo simulations of the MoEDAL experiment, the Schwinger monopoles, which are generated using the free particle kinematic distribution, which treats the time dependence of magnetic fields exactly. And the simulation code is developed in Gauss, which uses Geant4 as the simulation engine. The following is the visualization of Geant4 simulations of the MoEDAL experiment. You can see the monopole trappers, which are placed on the sides of the Velo LHCb vessel, and entities which are placed in forward and the top regions of the MoEDAL intersection point 8. So the magnetic monopole ionization losses, geometry, and material content is modeled in the simulations. And then monopoles are propagated using these, propagated through the MoEDAL detectors, and the acceptance or the efficiency is calculated. So here, just to give an idea about the trapping efficiency, it's a very simple figure. We use an isotropic momentum distribution, which has momentum values from very low values to about 1 TeV. And we use a mass of monopole, which is about 75 GeV, which is approximately in the range of masses which are expected to be produced in these collisions and expected to be detected by the MoEDAL experiment. So the monopole trapping efficiency is given by the ratio of the number of monopoles trapped by the MMTs to the total number of monopoles generated in these lead-iron runs. So initially what happens in this figure, as you increase the momentum distribution, the trapping efficiency increases because more and more monopoles are energetic enough to reach the trapping detectors and get trapped by the aluminum trappers. But as soon as we reach a threshold and increase the momentum values further, the trapping efficiency decreases because now the monopoles are energetic enough to punch through these trapping detectors. And so this reduces the efficiency of the MMTs. The main quantity which we are studying here is the mean Poisson rate, which is the rate of expected monopoles in the heavy iron run. So this uses the SCHWINGER cross section, the luminosity at intersection 0.8, and the trapping efficiency, and therefore we get the rate of monopoles which are expected to be produced in these collisions. The integrated luminosity over the heavy iron run was 0.235 nanobarns at MoEDAL intersection 0.8. And this is what we use. So the results of this experiment are expected very soon. And currently I can give a review of the ongoing work because it's still in the publication stage and before that. So both the monopole photon coupling and the space-time dependence of the electromagnetic fields would increase the overall production cross-section. So the cross-section approximation discussed in this talk would give a lower bound on the expected monopoles to be produced at the 2018 lead-iron run. These monopoles are generated using the SCHWINGER free particle momentum distribution, the SQUID measurements, the interferometer measurements for the monopoles, the Monte Carlo simulation and an analysis of data is almost complete and it's ready for publication. The results are expected to be released very soon. So just to give a summary of the significance of this search, this would be the first time magnetic monopoles have been searched for in heavy ion collisions via the SCHWINGER mechanism. The first experimental search where monopole cross-section are based on non-perturbative calculation, and therefore the calculation does not suffer from the strong coupling issue that the trillions cross-section face in the previous searches. These are the first collider searches where the produced monopoles are not assumed to be point-like because the exponential suppression does not apply for the composite monopoles. The current search, therefore, is the first study where monopoles are potentially detectable because of all the above reasons. The only previous experimental search for monopoles in heavy ion collisions was the one done in '98, which was the production of monopole pairs via thermalized quark-gluon plasma in the SPS collider, and this gave upper bounds on the cross-section of these monopoles in the heavy ion collisions. So that would conclude my talk. If there are any questions and comments, those are welcome.
Thank you, Aditya, for this nice talk. Marco has a question.
Okay, my question might be a bit naive or stupid because maybe it was answered already, but I'm wondering so these monopoles, how long do they exist for? I mean, what's their lifetime? So maybe Artu knows this, or you know this, I don't know.
So the monopoles, the various properties of these monopoles, these are supposed to be stable particles, and therefore as these particles are passing through the MoEDAL detectors, they would be trapped and they would stay in these detectors, which could be detected using the SQUID interferometer. So these are, yeah.
Stable on a scale of days or years, millennia? Because I'm wondering, the universe had pretty extreme conditions. So wouldn't these have been, if they're permanently stable, aren't there some early universe constraints on their existence, or would they be too diluted by cosmic expansion? Okay, I don't know if this doesn't really, I'm just wondering, because you said that they're being trapped and collected. So I thought, okay, they're stable. So if they're stable, then I realized for how long they're stable and how long do they hang around, Yeah.
So the lifetime of the monopoles in these trapping detectors was calculated, I think it's about 10 years or from some estimates. But
yeah, can I just jump in there, Aditya? You're talking about how long they're likely to be trapped,
yeah.
But the lifetime is essentially infinite as far as anybody knows, and that's the reason we have the monopole problem in the early universe. But there are lots and lots of cosmological studies on this that I don't think we can go into. Yeah,
but those are usually different kinds of monopoles. So maybe because there's like, okay, there are topological defects from some grand unified theory.
Well, these could be topological defects. I mean, in a sense, so we don't know. Yeah.
So the magnetic monopole from the early universe would be avoided for the same reason as the gut monopole problem. Okay, good. Because I think that
inflation was, as you know, inflation was introduced to get rid of the monopole problem, which would have been produced massively at the beginning of the universe in gut models. So there are lots and lots of
I don't want to
monopoles, so on and so forth.
I don't want to take too much time on this, but I'm just wondering, the gut monopole has an extremely high energy scale, typically guts. So inflation can solve this problem because it dilutes them, right? Here we are talking about things that can potentially be made at the LHC. So in cosmic history, there would, I guess, naively be made much later. So I'm not sure if inflation can save us here, but okay, I'm just thinking out loud. So maybe I should shut up for the moment.
You should. Do is I'll send you some papers where they have considered the problem of something like an electroweak monopole, and how would that be a problem? And there are ways of getting around it, of course, and I'll send you papers on that.
If I could very quickly add in relation to the question as to whether a monopole that's not a topological soliton would be stable, I believe that say an elementary Dirac monopole would still be stable for essentially an infinite amount of time because of conservation of magnetic charge. So the only way to destroy it would be to annihilate it with another monopole or to throw it into a black hole.
Absolutely.
Okay, thanks.
Mateusz has a question. I have a question myself. Go ahead, Mateusz.
Hi, yes, interesting talk. So I have a quick question on slide 12, where we discuss the momentum distribution. So what do you exactly mean by the momentum? Is it just the energy distribution of the monopole, or you also take care of the direction?
So the direction is, so the momentum distribution is supposed to be isotropic, which is generated from this, the free particle approximation case. And it takes care of the energy and the direction, which is for the monopoles. So this is basically the momentum distribution that we use in our simulations for the kinematics.
Okay, and did you try to compare it with leading order calculations, for example?
With what again? Sorry, I didn't.
Well, the calculations from the Feynman diagrams you.
The Drellian.
Well, not the Drellian. Gamma to a pair, right? Because this is the predominant process.
The photon fusion. So the momentum distribution has so it's not as energetic, I would say, as the Drellian or as the momentum distribution you get from the Drellian or the photon fusion case. So these monopoles are fairly less energetic than those cases, but the distribution is isotropic.
I was wondering about a couple of experimental things. You said that you have data of 0.2 inverse nanobarn of lead. How is it that the Atlas integrated in the last run 1.7 inverse nanobarn and you have only a fraction of this?
This was the luminosity at the MoEDAL intersection 0.8, 0.235 nanobarns. That was taken from a few sources at intersection 0.8.
Sorry. Yes, this is, of course, yes.
LHCb.
LHCb, yes, of course, yes, I was. And the second question is, why do you use only the MMTs and not the nuclear track detectors for this analysis?
So the nuclear track detectors is an upcoming analysis. For the past MoEDAL papers, the MMTs have only been studied for the monopoles, and an NTT paper is coming up with the results from the MoEDAL experiment. So this would be the next thing to do after the search for monopoles with the MMTs. Entities would be the next analysis.
But what is the difference between the two detectors? Do they have different capabilities or different? What I don't know. Why don't you combine? Is this I mean, do they cover different regions or of phase space, or what is the motivation of?
They do cover different regions of the space, and NTDs have greater acceptance to the monopoles than MMTs and the parse searches. So NTDs would improve, let's say, the mass bounds or in future searches. But those so the NTDs are being scanned at the current MoEDAL experiment for the past few results, and there should be a result coming out and an NTD searches very soon.
Can you give an idea what type of plot are you going to produce? A limit in terms of setting limits? Is this a mass plot as a function of what? What is the type of plot you are planning to produce? What is the takeaway?
It's a function of the monopole magnetic charges. So the masses as a function of monopole magnetic charges would be something.
Okay.
But the results are still awaited, so it should be.
Yeah. No, I was wondering.
Yeah.
So yes, okay, the same that you had in slide 6, basically. That's
yeah, something like that.
But okay. What is your?
But the range of masses would be.
Yes, this was my question.
Fairly low compared to the TV scale results and trillion. But then again, in the trillion we have because of the non-perturbative nature, you can only place upper bounds in the cross sections.
But then, how low in mass can you go? Maybe the question is not on the upper limit, but in the lower limit.
Because of the magnetic fields which are present, these are very strong. These bounds should be greater than the bounds for at least the magnetars and the SPS, as we had seen in the previous presentation by Professor Ajante. So these bounds would be greater than those bounds, of course.
Okay, thank you. Any other question? If not, let's thank Aditya again, and let's move to the next talk.